A very good afternoon to all of you. Today we are going to start week 10 of the problem solving session for the course Advanced Soil Mechanics, which is being taught by Professor Sridhar Shekhan, who is the professor at Department of Civil Engineering, IIT Guwahati. I'm your teaching assistant, Mujibur Rahman, from the Department of Civil Engineering, IIT Madras. So today we are also, like in the last session, you have seen we have introduced you to the concept of critical state soil mechanics. So we'll be extending that in this session also. So just a brief what we are going to do in this. We just want to understand that what is the starting point of the given soil or the state of soil with respect to the critical state, or when a soil reaches the failure, how we can represent that failure in terms of the or what is the state of the soil which was the critical state at the failure, and also like it's important to know that in the critical state framework, the failure would occur in the soil when the state of the soil reaches the critical state. So this is the I think conclusion that we made in the last week also. The failure occurs when a soil state reaches the critical state. So we want to know that where the position of the soil is initially, so that it will help us to understand the factor of safety that is available for the failure. So we'll start with the um, with some like in the last session we have like we introduced you to the concept that this there can like we have introduced you to the bounds like this NCL normally consolidation line. There is no state that is possible above this NCL. Like in this state, there is no we can't expect a state above this normally consolidation line. Correct. So all the soils which are normally consolidated, they fall on this blue color line. And below this, there can be the two states which can occur. Either it can be a lightly over consolidated or heavily over consolidated. Fine, depending on the stress state that it has gone under during the unloading stage. Now there is one another ratio like the over consolidation ratio. We we describe it as critical over consolidation ratio line. Critical over consolidation ratio line, which actually separates the lightly overly consolidated and heavily overly consolidated. It's you can see it's close to the critical state line, and above this COCRC, we have the lightly overly consolidated, and below this COCRL, we have the heavily overly consolidated soil. And the value of the COCR, critical over consolidated ratio, it depends on the soil type, and in general, it has been considered as 2, right? And the region which is on the right side of COCRL, on the right side of COCRL is the LOC, or we call it wet side, and on the left side we have the dry side, similar to the like in the OMC we used to study that wet side and dry side. And generally in some textbooks you would found that this COCRC, they refer critical state line as the COCRC, and they used to describe the state of LOC and HOC based on the critical state line. After that, we have the like we have studied the undrained shear strength, like in the UU test, unconstrained undrained test. So how the undrained strength can be expressed in terms of critical state parameters? That's what we want to do it here. So we know that in a critical state soil mechanics or the CS framework, the failure occurs when the state of the soil reaches the critical state. Fine. So at the state of failure, or when the soil reaches the critical state, we can express the tau failure is equal to tau critical state given by sigma critical state and tan phi of critical state, phi dash CS. Fine. And now if you look at this plot, which is tau versus E, it's obvious that as we increase the wide ratio of the soil, the strength of the soil is going to decrease. So this S, or the strength, is depending on the void ratio. And also we know this relationship, S is equal to WG. For a saturated soil, S is equal to 1, and G is a like specific gravity of the soil, which is constant. So E and W, which is the water content, are related. So if E increases, water content also releases. It means that strength has a relationship with the water content also. So it means that the undrained shear strength, it refers to the strength when the soil is sheared without changing the water content. So undrained shear strength, as we know, that we are not allowing the drainage to happen during the undrained sharing. So whatever the strength the soil have, it will be having at a constant value of either void ratio or the water content. And also, we know that when we talk about the undrained UU test, we have told that we have told that there cannot be a effective Mohr circle or effective Mohr circle. There was only one effective Mohr circle for the effective case. But in the total stress, we have seen there are, depending upon the confining stresses, how much we want to test, there are that much of this Mohr circles. But for whatever the confining, for example, we have three confining stresses. For all the three confining stresses, we are achieving only one effective circle, effective Mohr circle, correct? And with that effective Mohr circle, we are not able to draw the failure plane. Fine. We were not able to draw the effective failure plane. Correct. So now the thing is like if you know the 5-day CS of the soil and Tresca failure country as per the Tresca failure country at SU is equal to sigma dash tan of 5-day CS. The intersection of these points, one is this SU, the equation for the SU as per the Tresca failure criteria, and the effective Mohr circle and the effective Mohr circle failure line, we'll be able to discuss about this point SU, which can be given by sigma dash CS tan of 5 CS. Now this tau F is given by the tau dash CS as per the uh, critical state framework, that the failure state is equivalent to the critical state here. It is given by SU, undrained shear strength. Now this SU is equivalent to sigma dash CS tan of 5 dash CU, correct? Now this E as the critical state can be written as E gamma minus CC log of sigma dash CS. Like in the last lecture, we have seen how this can be written in this form. Now this sigma dash CS, we replace the sigma dash CS by the value which we can obtain from this equation, correct? So once we replace this, we will get the equation log of SU divided by tan of sigma dash CS given by E is equivalent to E gamma minus ECS divided by CC. Now in this equation, you see that this SU, it changed with the void ratio, or it is a function of void ratio. Or we can say this SU is a function of water content also. It's a state dependent parameter. So this SU or the undrained shear strength is not a fundamental parameter. It's a state dependent parameter. State dependent parameter means it depends upon the initial state. What is the initial void ratio? What is the initial water content of the soil? So we can't consider this as a fundamental property. Fine. Now we want to discuss the critical state parameter in terms of QP plot. Last time we have seen the critical state parameters in terms of the E, P, and mu. Now, in terms of the shear stress, tau, sigma, and mu, which is the specific volume. Now, in terms of the Q, P, and V, which is the specific volume, the response seems to be similar. Only the formulations are going to change. Now, in the critical state framework, when the soil reaches the failure state or the critical state, the equation Q is called MF becomes valid, in which Q critical state is equal to M times P dash critical state CS. This is similar because we are telling that the soil will reach the failure when it reaches a critical state. So both the equations are valid in the critical state framework. And the slope of this line, it's given by 6 times sine of 5 dash CS divided by 3 minus sine of 5 dash CS. It's like in the I think in the last lecture we have seen this, how we can determine the slope of this QP. When we talk about the QP representation few weeks back, so in that lecture we show how this can be obtained. Now we know, like if we have this V ln P plot in which this is NCL with a slope of lambda, and this is the critical state line with the same slope of lambda, and uh, corresponding to the P dash CS, which is the like when the soil reaches the critical state, the P dash final or the failure is given by P dash CS, and corresponding V is given by VF, given by VCS, and the corresponding Q is given by QCS. Now, for the for initial P dash is for the very low confining stress of 1 kPa, mean effective stress of 1 kPa, we describe two parameters N naught and gamma. which are actually the intercepts for the like specific volume at for the NCL line and CSL line. Correct. So equation of CSL in V ln of P dash plot is given by VF, which is this. It can be given by the lambda, sorry, gamma minus lambda times ln of P dash FC. Fine. So we have to reach here. So we are here. We will subtract this part to reach the here. Correct. So now the parameter lambda M and gamma are independent of initial state because they represent the critical state. Fine. And can be considered as the critical parameters. Now we know that this lambda, M, and gamma, they are the critical, they are the fundamental properties. So can we use these parameters in order to get this untamed, like we get this untamed shear strength, which is in terms of state parameter E and ECS or CC, which are not fundamental. So we'll change that so that we'll get a we will get this SU in terms of state in terms of critical state parameters. We know that SU is given by Q by 2. If you know this, so this strength is given by Q by 2. So QF can be written as M times P dash F, and this P dash F can be written in terms of these parameters. Fine. So ln of 2 times SU by M is equal to gamma minus VF divided by lambda, which the untamed shear strength in terms of critical state parameters. Now for each plot, like we have this point is here, it has a coordinate in P and Q, and same plot has the values of P and F in this plot. Fine. Now we want to normalize the plots in order to make them independent of the initial conditions, like independent of the state parameters. Now, for example, if we take a point P and the state of P is defined by PP dash, which is the mean effective stress at this point, VP lambda, VP is a specific volume for this point, and similarly QP. Fine, and we can normalize it either by the normalizing parameters can be PP dash and VP lambda, or it can be PPM also. However, considering this PPF is more convenient because the distance between the PPC and PPF, sorry, PP, the distance between the PP, which is the mean effective stress at point P, and this PPC, which is the mean effective stress at the critical state, will tell us about the factor of safety. So it's more convenient to use PPC rather PPM. Correct? Now, for this point P, we can write the specific volume as Vp lambda minus lambda times ln of Pp dash. Now, this Vp, we need to determine the value of Vp lambda. So, Vp lambda is equal to Vpa plus lambda times ln of Pp dash. So, Vp is known to us, and lambda is actually the slope, and this ln of Pp dash, it's known. So, this Vp can be also written as gamma minus ln of Pp dash. Fine. So Vp, it can be written in this form or in this form. For this, like it's from the critical state, it's from the state of the soil. Now Vp is equal to gamma minus lambda times PPC or P dash PC, which is the critical state mean effective stress. So ln of PPC is given by gamma minus Vp by lambda. So by normalizing both critical state and then a normally considered line will appear as a point. Now, what it means that if we normalize this plot ln P and this Q, PP dash by PPC and Q divided by PP dash, we'll find this CSL critical state line and the normally consolidated line will be a single point there. So along CCL, if you find this along this CCL, whatever be the P, it will be equivalent to P critical, correct? P dash P critical, like whatever be the P, it represents the critical state mean effective stress along this line, correct? So it means that P dash is equal to P dash PC, and the value P dash by P dash PC will equivalent to 1. And the ratio of Q by P will be M, the slope of this line. Fine. So it means that this point will be at a distance of 1, correct, from the origin, and at a slope of M. Now, if we talk about the NCL, NCL to be isotropic, if like NCL is isotropic, normally consolidation line, it means Q by P dash will be 0 because Q is 0. So in that case, you will see that it will always lie on along this PP dash P dash by P dash PC line. So P dash PM divided by P dash PC is a constant, and it will be always along the NCL, and along and always NCL will be represented by a point. So this will be always a point, and this will be also always a point. So by normalizing this CSL and NCL, the like the understanding becomes a little easy. Fine. Now we have seen the effect of state. Like in here, we have seen that SU is a state dependent parameter. Later on, we have considered it as a change it to the critical state parameters. Now, this state of soil is also playing a important role in governing the shear strength and the stiffness with respect to the like void ratio, water content, pH, and OCR. So it's also dependent. It also affects the state. It also affects the strength and stiffness, like the other parameters are affecting. Now, the state of the soil defines the initial point from the CSL. Now, state, what do we mean by state? If we tell about like we have the critical state line, and we want to know about the state of the soil. So how far is the initial state? How far our E and E is from the critical state line, like in terms of E versus log P plot. That defines the initial point, like that defines the state of the soil. How far is the current state from the critical state line? So state of soil defines the point from the critical state line. For example, if we have point P, so if we want to know the state of this point, so we have to determine the distance, how far is from the critical state line. Let's assume this SV is a vertical distance between the CSL and point P. So it's equivalent to, if you see that this is a parallel line with all the three lines have the same slope of lambda. So the distance between the gamma and this the difference between the gamma and VP gamma will give the SV. Correct. So SV is given by gamma minus VP lambda. Now the horizontal distance between this horizontal distance of point P from the critical state line is given by what is the P at the critical state and what is the current P. Fine. So ln of, it's given by ln of, because this is in the logarithmic, it's a similar logarithm plot. So ln of SS is given by ln of P dash PC minus ln of P dash P. So you will get SS, which is given by SS is the horizontal distance of point P from the critical state line, which is given by PP P dash PC divided by P dash P. So also SV by lambda, which is the slope of, like for example, this is a horizontal distance, this is a vertical distance, and this has a slope of lambda. So it's actually determine the slope. So SV divided by ln of SS is given by lambda, or SV is equal to lambda times ln of SS. So we have SV also, we have SS also. So this will determine the state parameters of the point P, which will tell us how far it's from what is the initial point from the critical state line. Now, state parameters are also related to critical state line, and SS is similar to OCR. It's like the OCR, present by past. Correct. Now, quick summary that in the critical state framework, we are only taking the effective stress parameters in consideration. We are utilizing the CC compression index, the effective stress inherent stress paths, primary consolidation parameters CV, MV, lambda, kappa, and the shear strength parameters Q, P dash, M, phi dash. And these formations we have derived. Correct. Now we want to write CC and MV in terms of lambda and specific volume. We know CC is equal to minus dE divided by like change in the y dash divided by change in the log of V dash. And this E can be written in terms of V is equal to 1 plus E specific volume. So the change in V is equivalent to the change in E. And this D log of P dash can be written in terms of ln. Correct? So which is given by 1 divided by 2.303 change in ln D of ln of P dash. Correct? So once we differentiate this, we will get minus 2.303 P dash dV by dP dash. Now we know this V, which is a specific volume, is given by and not minus lambda ln of P dash which is actually the specific volume considering the normally consolidation line. So once you differentiate it, dV is equal to minus lambda times dP dash by P dash. So we'll get a value of dV divided dP dash, which we can replace here. So we'll get the CC is equal to 2.303 lambda, and CR for the swelling reloading line See, it's going to be 2.303 kappa. Now, if we talk about MV, MV is equal to minus change in E divided by 1 plus E naught dP dash, and this dE can be written as dV. So dV divided by dP dash is equal to lambda divided by P dash. So MV can be written as minus lambda divided by P dash into V naught. Why? Because 1 plus E naught will represent initial stochastic volume. Correct? So we have written the this consolidation parameters also in terms of the critical state parameters. Now, how we are representing the different like the test is we have done the different tests in the triaxial, how we can represent in the 2D like the critical states soil mechanics in the CSM framework. We will start with the 2D representation first. Now we have a, for example, we have the three critical, this is a E versus sigma plot and corresponding tau versus delta and tau versus sigma dash plot. Correct. Now we have three identical clay specimen which are subject to the consolidated drainage shear test for three different sigma dashes. So we have done three drain tests and add three confining stresses. So it means that when we are doing the drain test, whatever be the mean effective stress, it will remain, or we can say this normal stress is remaining, effective normal stress are remaining constant in this test. Right? It's a drainage test; it's not going to change. Now, what actually changed? If it's a drainage test, the volumetric strain will be there. It will get there will be the pore water pressure is not going to develop there. So whatever the change in the volumetric strain, it will change the void ratio. So you'll see that at the three tests you will see vertical drops in the E versus sigma plot, which actually shows that the soil has undergone a volumetric strain till it reaches the critical state at all the three states. So in terms of tau versus sigma dash, you will see that only tau is shear stress is increasing without the change in the effective normal stresses. And this change is brought by the change in the void ratio. So it means that if we are doing drain test, and the tendency of the soil is to contract since it's an NC soil. So this it can reach the critical state by changing the void ratio, by reducing the void ratio and reaching the critical state. Fine. Now, for example, we have now the undrained steering for the NC soil. Now, NC soil has a tendency to contract. So there will be a generation of it's a tendency to contract since the drainage is not allowed. So what will happen? There will be a generation of excess pore water pressure, which will try to reduce the effective stresses. Now, if this is the initial state of the soil, fine. So it has to reduce. It has to reach the critical state. So the only way of doing is to by reducing the mean effective stress. That is possible by generating because this is possible because there is a generation of excess pore water pressure which is actually reducing the effective stress. And you can see that how this thing looks in the tau sigma dash plot. It starts with the initial sigma dash n naught, and due to the generation of excess pore water pressure, it's reducing and reaching the critical state. So you can see in the undrained condition how the soil is reaching the critical state from the normally consolidation line. Fine. It was for the NC. Fine. Yeah, and also like for the NC we have zero cohesion. Now for OC, OC means poorly consolidated. So first, the soil is brought to the OC state. It means that the soil is loaded, then unloaded, and reached to point P, which is our point of concentration. Now, in the OC, in the overly consolidation, which is the OC over consolidated soil is in the drain test. What will happen in that? There, the void ratio increase due to the dilation. Now, there is no change in the normal effective normal stresses. So the dilation will actually increase the volume. It actually decreases the volumetric strain. Sorry, it will increase the volumetric strain. Fine, it increases the volumetric strain, or we can say that the void ratio is increasing. So that is bring by increasing void ratio. So how the NCL state will reach the critical state at a constant sigma feeder, it will increase the void ratio till it reach the critical state line at Q. Fine. So also you know that for the OC soils. For the OC sites, it will achieve a peak first, then undergo the yielding till it reaches the failure. Fine. So now that's actually visible here. You can see how for this drain case in case of OC, the soil starts from sigma p, it reaches the peak state. This is a failure line comes to the peak state, and then once it returns back, it fails at here. Fine. You can see how it goes. Now, this peak state, it depends upon the over consolidation ratio. For some soil it may be very steep, for some soil it may be like it depends upon the OCR of the soil. And once it reaches peak state, it has to yield to reach the critical state. So that brings actually the concept of yielding here. So in HOC, soil reaches peak state before reaching the critical state. Now, how this undrained sharing will look like? Fine. So undrained sharing of OC soil results in the negative pore water pressure. It means that if we are here, correct, if we are actually here, and we have to reach the critical state without the change in the void ratio. So the only way left is to go to right without the change in the void ratio because it's undrained test. So due to the generation of negative pore water pressure, the this stress or this the point P we reached the Q. So in terms of this is like a E versus log sigma. And in terms of tau versus or stress strain plot or peak stress representation, the QP starts here due to the generation of negative pore water pressure. There it reaches point Q, correct? And this shows the dilation. Now, the point of intersection of unloading line with the COS. In undrained there is a point P for which delta is zero. Like in the undrained case, I will show it here. There may be the chances that when rest is it is initial U naught, it's initial U naught. In case it starts to like when we do the undrained sharing, there are the chances that there will be initial generation of pore water and then it starts to decrease. So the change delta U, or you can write it like this simply. So delta U plot, it is like there's a generation of power to pore water pressure initially, and then it starts to decrease and remain negative. So there may be the state where the like there's a point P at which the or the stress at which the delta U is zero in the undrained case. So it means that there is a stress state which corresponds to this point where the delta is zero, and this point is the intersection of what is it? It's the intersection of unloading line with the COCRC. Fine. And the right side of COC, if the state of the soil is on the right side of COCRC, the positive pore water pressure will be generated and like during compression sharing. And like left side of COCRC, which is the heavily water consolidated, so there will be the generation of negative pore water pressure, which actually brings the state to the right side, like this. Fine. Now, this was in terms of the E sigma dash and tau. Now, in terms of PQ and uh, specific volume, the 2D analysis of NC soils are related to CU and CD in VPQ dash plot. Now, A corresponds to the initial like isotropic consolidation state. Now, when we are doing the drain test for the NC soils, so the slope of this TSP and ESP in terms of since if it's a drain test, then the total stress and effective stress path will be same. So it will go like this, correct? And from the V ln P dash, if this is the NCL or isotropic consolidation line, so this point will fall here. If we are doing the drain test, then the soil has a tendency to reach the critical state with a slope of 1 is to 3. It reaches a critical state at B, which is represented by the here in terms like by reducing the volume or by undergoing the volumetric strain. So it is an soil. So volumetric strain will be there, and as a result of which we can see there is a compression. As a result of which the specific volume will decrease, and the point which is here B dash you can represent by B double dash either in the V versus on P dash plot. Now, if we have a undrained situation, in the undrained situation, what will happen? There is a generation of excess pore water pressure, which will actually reduce the effective stress. So this effective stress path will move to the left. Now, effective stress moving to the left means at a constant specific volume, there will be a decrease in the mean effective stress. So it means that from here to here, the soil will reach from A to C double dash without the change in the specific volume because it is a undrained, consolidated undrained test. Fine. So there will be the generation of excess pore water pressure, which will reduce the mean effective stress, what was present at A dash. So it can be represented by A dash C double dash. Correct? Fine. Now, similarly for the OC, how it looks for the OC. The OC exhibits peak and critical state, like it is a peak and critical state. Both needs to be accounted in the critical state soil mechanics. So now the soil is initially isotropically normally consolidated and unloaded to P dash C, and point D is a heavily only consolidated. Now, for example, that we have once we have started the soil to load and unload, the point D represents the point which is the heavily overly consolidated here, correct? So we know that if it's a heavily overly consolidated, it will be somewhat on the left side of the CSL. So this point can be represented by this D double dash point. Now, when we start the doing the drain test, what will happen that it will go with a slope of 3, reach the peak state, which is a peak line corresponding to the OCR or corresponding to HOC, U dash H. It will reach the peak state, P dash, correct, and then comes back to F dash. Now, during this DT, there is an initial contraction, the specific volume starts to decrease, and then it will start to increase also when the dilation starts. So E double dash F double dash represents the dilation, and this D double dash to here it represents some amount of contraction that is occurring in the OC, and after that there will be a dilation, correct? And you can see with this QP single QP plot, the information regarding the volume was missing. So that's why this critical state soil mechanics, it actually it helps us to visualize the things more properly as compared to the more column theory knobs or the simple stress strain plots. Fine. So during shearing, specific volume first decreases and approaches peak E double dash and then increases to dilation due to dilation and fails at CSL, which is the F double dash point. Now, in case of undrained condition, what will happen? So ESP and TSP will be different because it's the undrained case. So this D dash and D dash will be a similar point, same point here. So now this is a total stress path, correct? It will go here to E dash and then reach the failure, similar to the previous one. But if we talk about the effective stress path, what will happen? At once there will be it will be like there will be the generation of negative pore water pressure, correct, in the undrained or a positive pore water pressure. So which will affect the effective stress path. So what will happen then? The ESP will first touch the DG, like it will reach the peak line at G dash. On further sharing, U tends towards negative and meets the critical stand at I dash. So there will be the increase in the effective stresses, which will shift the ESP to the right and touch the critical state at I dash. Now, due to this, since it's undrained condition, so specific volume is not going to change. So the only change that can happen is the in the mean effective stresses, correct? So that's why you can see the mean effective stress is mean effective stress is going to change. It moves to from D double dash to D double dash and then to I double dash at a constant specific volume at, let's assume V naught, correct? Now you have seen that we have the bounds. We have defined the right side bound with the NCL, like we can't go beyond this NCL. Now similar to this, when we are unloading the soil, when we are unloading the soil, we cannot unload it simply. There should be a bound for it. So generally, like if we have three states of soil A, B, C, and this A is a low tensile zone, and like the reloading is less. B is medium tensile zone. There is some reloading, and C is the high tensile zone. When we are applying the reload on the sample, and we are going to a large extent. Though, so we can't go beyond this, or we can't. Where should we stop? Should we stop here, 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 or where? So for considering the bound on the left side, we are assuming a line O U dash, which is actually the left side bound, and the slope of this line is given by OU dash is a tension bound failure tension bound. Beyond this, there will be a tension failure zone, and the zone from which starts is OU dash. Like this zone is a there will be no tension fail, but if we go beyond this OU dash in the reloading, there will be a failure. So the left of line OU dash is a tension failure zone. Failure stresses would become negative. Soil state is not possible in tensile failure zone. And the slope of this line OU dash is 3. So line OU dash to slope 3 limits the soil to non-tensile failure zone. So we have now two bounds. One is the critical state bound, one is the here, and one we have found with the OU dash line with a slope of 1:3. So beyond that, we can't unload the sample. Now, since we are telling that the critical state is the ultimate state, so whatever the state a soil can have, it should lie on it. So critical state limits all possible states of soil irrespective of stress, state, drainage, condition, loading condition, which was not present in the earlier PQ parts. Now let's justify these statements. and all effective stress paths finally reach the critical state line, which is unique for a particular soil. It means that all the effective stress paths, whatever the effective stress, whatever the loading conditions you will impose on the soil, so they all will reach the critical state line, which is the fundamental property of the soil, this CS. For example, if we take the light overly consolidated soil, and A is the initial condition. So lightly overly consolidated means it will be somewhere between the NCL and CSL. Correct? Now AB represents the UU test. UU test means unconsolidated undrained test. So what will happen is undrained test, if it has reached a critical state, it has to there will be generation of positive pore water pressure as a result of mean effective stress degree, and the soil state reaches failure or CSL at point B. Now AC represents the consolidation phase. So A is the initial state, and once we are doing the consolidation, two things are happening. We are, for example, we have to reach a consolidation pressure of 100 kPa. So first thing that will happen is that consolidation pressure will increase to 100 kPa, and with the increase in this 100 kPa consolidation pressure, when we allow the soil to consolidate, the void ratio will decrease. So or we can say there is a decrease in the specific volume. So that's why you can see from A to C there's a decrease in specific volume, and also there's a small change in the mean effective stresses. CD represents the consolidated. CD is the consolidated undrained sharing. CD. Now from C, if we are doing the consolidated undrained test, so again after consolidation we are not allowing the drainage to happen. So there is generation of excess pore water which decrease the mean effective stress and reach the critical state without the change in the specific volume. CE is a consolidated drained sharing. So what will happen? There will be change in the specific volume and at a constant. There will be a small change in mean effective stress, but the main thing is the change that is visible is the change in the specific volume due to the compression. So A, C, D, A, C, and D is the like the critical state representation for the consolidated undrained test, and ACE is the representation for the entire consolidated test. And you can see all E, D, B, they are the critical states of the soil, so they can be represented on a single CSL for the soil, which is a unique for a particular soil. For NC, the trends are same except that E and C will be on NCL. Okay, like this is considered for some soils, but if we have normally consolidated clay, so it can this A will shift to here and A will shift to here and C will shift to here. The only difference will be there. Now similarly for the heavily overly consolidated, if F is the initial condition, if F is the initial condition, since the heavily overly consolidated, it will be on the left side of CSL, correct? FB represents the UU test. So FB, if it is a UU test, there will be an increase in P dash due to the generation of negative pore water pressure at a constant specific volume. FG is a consolidation phase. FG is a consolidation phase, correct? Decrease will be there in the U due to the compression, and simple like increase in ln of P dash due to since it has reached a consolidation state. GH is the consolidated undrained sharing. GH represents the consolidation undrained sharing because I can see there is no change specific volume and the mean effective stress increase due to the negative generation of negative pore water pressure. So FGH represents the entire consolidated drain test, and FGI. So FGI represents the consolidated drain test. So what consolidated drain test? FG is the consolidation from G. We are allowing the drainage. So there will be initial contraction. After that, there will be a dilation, as a result of which the specific volume will increase. So point A and F soil state have same specific volume and different stress history. A and F. You can see A and F, they have the same specific volume, but the stress history is different. For undrained failure stress P dash F at B are same here. So for undrained sharing, so we are going from here to here or from A to B. The P dash F is same for point B. So NCL and LOC approach CSL from right side, wet side, and HOC approach CSL from left side. It means that normally consolidated or lightly overly consolidated soils, they are approaching the critical state from the right side, which is called the wet side, and HOC heavily overly consolidated are reaching the critical state on the left side. So whatever be the initial state, stress history, and loading condition, the final state approaches the ultimate state, which is the critical state. So that's what I want to tell you. I want to discuss about this point that the initial state, whatever be the void ratio, whatever be the water content, or whatever be the stress history, that is the OCR, or whatever be the loading condition, whether you are doing the CD, CC, and whether you are doing the CCC, the consolidated drain or consolidated test, the final state, which is the BH DEI, it will reach the critical state, which is a unique for a given soil. Now, uh, initially, when we talk about the bounds, in just few I think few minutes back, we discussed about some bounds. Right sound bound is the normally consolidated line. We can't expect a state on the right side of this NCL. Similarly, we have bound on the unloading also, like the tensile failure zone. There is a line O U dash which has slope of one which has a slope of 3. So now in the like in the upside, what is the bound? The upside bound is the top bound is the peak state, correct? So if we talk about this peak state, let's consider 2 points, E1 and E2, and E2 is greater than E1. Fine. Like I'm going to say, like the void ratio E1 is greater than E2, and this E2 will be kind of it will have a high strength because it is likely having a high density as compared to E1. So shear test is conducted at identical E at different confining stresses. So for E1 also we performed a different tests at different confining stresses represented by R and S. Similarly for E2, peak state line meets CSL at S and Q, and for this E1, the peak state lines reach the Q. For E1, it is S at point S, the peak state reaches the critical state line, and for E2, it reaches at point Q. So you remember that this peak state line is actually it represents the effect of dilation in the sample. So rather than following a straight line, it's a curved line. This is due to the dilation, and we know that as we increase the mean normal stress, the dilation terminates or it suppresses. So peak states are terminated at P and R at low sigma dash, and in here on the left side they are they are terminated at P and R, and these states it doesn't follow the Coulomb's equation at low sigma dash. So at lower values of sigma dash, this is not going to follow the Coulomb's equation. Now the thing is like how this can be visualize it in another manner. Like if we are normalizing them, with normalizing, we are actually overcoming the effect, we are neglecting the effect of void ratio. Now, if we can see that when we have the normalizing parameter sigma c, which is the critical states normal stress. So once we normalize that, you will see that we will get all the stress states, peak stress states will fall on line PL, which has a slope at phi dash P and an intercept of C dash P. So all these parameters, C dash P, phi dash P, and can be written in terms of tau by sigma dash C and sigma dash divided by sigma dash C. And the equation we will get is this is the equation we will obtain. And the parameters Cp dash, phi dash, phi dashes are independent of the initial state of the soil. So these parameters can be considered as fundamental properties under certain conditions. If we talk about the only initial conditions, then these are considered as fundamental properties. But if we bring in the stresses or the confining stress into the consideration, then they are going to change. Now peak state in terms of V, Q, and P dash. Same exercise we are doing in terms of the spastic volume. So these are the equations. Again, parameter G, PV, MCH are fundamental property independent of E and void ratio. The contribution of E or water content is inclusive in P dash C. Now, if we talk about the this failure line for the heavily or consolidated states. So generally, granular soils which are not cemented will have a zero shear strength at zero mean effective stress. So it is apparent that peak line should pass to the origin. So if we talk about the cohesionless soils or the soil which have very less cementation or which have no cementation, then the shear strength line of the critical state line should pass through the or the failure line should pass through the origin, and also this failure line should meet the critical state line. So or the peak line, if we represent the peak state line, it should first pass the origin because it has a zero strength at zero confining stress, and also it should pass through the origin. It should pass through this peak line, should pass through the origin, and it should pass through the critical state line. So this is possible only when we consider curved line, because with the straight line it's not possible. Now, so peak line should also meet CSL, and it's also pass through the origin. So this can be achieved by the curved line power law, given by QP is equal to M P dash 4 is power B, which if we are log using the log both sides, you will get equation like this. And this MC and beta, they are the soil parameters. Now we want to compare the power law curve and the linear Mohr Coulomb curve. For that, we will take the two cases. In the case one, we will take three identical samples in the normalized plots, tau by sigma dash and sigma dash by sigma dash c. CSF will be a simple a point in this plot, as per the previous discussion. So if we want to, we can represent these, like once we draw the peak straight line using the power law. This is the power law line, peak straight line in terms of power line or a curved line, and this is as per the Mohr Coulomb failure envelope. Fine. The second case, the first case, A, B, C, the stress states or the mean effective stress are close to the CSF. And in the second state, you can see that stress states or the effective stresses are very far. They are close to the origin. Fine. So in case where data points are close to the CS, and in second case, data points are close to the origin. So you can see that in both the cases, MC1 and MC2, they do not pass to the origin. They are not passing through the origin, and they are also not passing through the critical state, but the power line is passing through the critical state and also through the origin. So not passing through origin is not applicable for cohesion of materials, and those soils with only apparent cohesion. So it means that if we talk about the cohesion of soils in terms of the M in the Mohr Coulomb law, then the information, then it's not a valid thing, it's not appropriate, because this Mohr law for the cohesion of material or the soils which have very less cohesion or apparent cohesion, it's not going to pass to the origin and the critical state. However, this is applicable for the true cohesion. In case the soils have true cohesion, then this is a valid thing. We can use this Mohr Coulomb envelope, because in that case we have some cementation values there. But if it is a purely cohesionless soil, then struct is meaningless for them. So not passing through critical state violates the fact the soil keeps dilating even at high confining stresses. So this you can see that Mohr Coulomb failure unlock, it doesn't pass to the critical state. It means that the soil it's going away from the critical state, which means that it is dilating for the high sigma dash. So the Mohr Coulomb parameters are conservative and overestimates the strength for the range of sigma beyond which peak strength is determined. You can see that for these points, the strength parameters, strength values given by the Mohr Coulomb envelope and the critical and the power law, they're nearly close. But for the curves like this and this, you can see this the Mohr Coulomb the Mohr Coulomb failure criteria is given the strength which is higher here also, and here also it's very high. It actually overestimates the strength. Now similarly, we have the comparison between the stress dilatancy and Mohr Coulomb envelope. For example, we will consider the four peak states B1, B2, B1, B2, C1, C2. Correct? B1, C1 have same wide ratio on the Mohr Coulomb line, Mohr Coulomb envelope, which is given by C dash P1, C dash P1, and phi dash P. Like once we will plot them here, we will get this parameter. B2, E2 has same E on and lie on the Mohr Coulomb failure line, and which gives C dash P2 and phi P2. You can see this one. You need to turn off airplane mode. After that, B1 and B2 have same sigma dash B, and B2 is more overly consolidated than B1. Now you can see there's this B1 and B2, even if they have this different wide ratio, they are at the same stress level. And similarly, C1 and C2, they are at same stress level. However, the over consolidation ratio is different, correct? And B2 is more OC as compared to B1, because the wide ratio of 8 E2 is less than E1. Now B1 and B2 would reach CSL at BC. Now this B1 and B2 will reach the critical state line at BC here, correct? Now B1 and B2 will reach the critical state line at BC. B2 had to dilate more than B1. Now, if B1 has to reach the critical state, it will dilate from here, correct? Now B2, its point here. So to reach the critical state, it has to dilate more as compared to B1. Fine. So B2, which is actually far from the critical state line, it has to dilate more to reach the critical state line. Now this B1 is close to critical state line because it's lessly over deconsolidated, so it has to dilate less. Correct. So B2 has higher dilation angle phi dash P than B1. It's correct only. You can see that this this is a phi dash P. It's for the B1. Now for this B2, if you draw a line here, it will be higher than the corresponding to B1. So B1 C2, B1 and C2 have the same OCR. They have the B1 and C2 have same over consolidation ratio, different E and sigma dash. However, they have different B1 and C2. If you consider these points, B1 and C2, they have different E, correct? But their over consolidation ratio is same, even if their void ratio and sigma d is different. So it means that why they have same over consolidation ratio? Because they have to travel to the same dilation angle to reach the critical state line. Fine, because their phi dash p is same, their dilation angle is same. It means that they are at same OCR, even if their void ratio and sigma is different. So B1 C2 has same dilation angle, which can be given by tau divided by sigma dash is equal to tan of phi dash CS plus dilation the phi dash psi dash B. So it's important to specify void ratio, OCR, dilation, tau, and sigma for analyzing and interpreting the test results related to the peak soil behavior. So for interpreting it means that for analyzing the test results corresponding to peak soil behavior, we have to take into consideration the initial state, the stress history, dilation, and the stress state. Correct. For analyzing the peak behavior. Correct. So it means that even if we have a different void ratio and the stress or the confining stress, those soils can have a same OCR depending upon the dilation. We can have same OCR depending upon they can have a same OCR even if they have different void ratio and sigma dash. Correct. Now we will solve some problems which are they are similar to the assignment problems which have been assigned to you. So once you will complete these problems, I hope you will be able to complete the assignment questions very easily and very quickly. So I will take a break here for 5 minutes. After then, we will start again. So till then, you can ask some doubts if you have. Then we can start again. So we'll start with the uh, problems. The first problem is a saturated clay has gamma of 3, lambda of 0.2, the critical state parameters. At critical state, the specific volume is 2.5. Determine the P dash at critical state. So these are this is the initial value of the uh, uh, critical state line, correct, for the soil. And lambda is the slope of the NCL. So we know the formulation. V is equal to specific volume is given by gamma minus lambda times ln of P dash. Correct. Now this specific volume is given by 2.5, gamma is 3.0, and lambda is 0.2. Fine. Now if we rearrange these terms, so ln of P dash can be written as gamma minus specific volume divided by lambda. So P dash can be written as E raised to power lambda gamma minus mu divided by lambda. So E raised to power gamma is 3 minus 2.5 divided by 0.2, which is E raised to power 2. I think it's 2.5. 0.5 divided by 2 is 2.5, which is equivalent to 12.23. Fine. This is simple like the equation basic question. Find the slope of Find slope of q by pq plot if q is 120 and p dash is the slope, which is given by m, it's given by q by p. What's q? It's 120 divided by 100. So m is given by 1.2. It's the slope. Or you can, from m, you can determine the pi dash also, or simple pi dash. Correct? Moving to question number 3. The soil has reached a critical state with the QCS is equal to 100 kPa and P dash CS is equal to 300 kPa. The critical friction angle in terms of degrees is again the same question. You are given Q critical state is 100 kPa and P dash, a mean effective stress at the critical state is 300 kPa. We have been asked to determine the pi dash CS. So we know that the slope of the critical state line is given by QCS divided by P dash CS, which is equivalent to 6 sine of pi dash divided by 3 minus sine of pi dash CS. Correct? So Q by P is 100 divided by 300 is equal to 6 sine of pi dash CS divided by 3 minus sine of pi dash CS. So on rearranging, we can do it 3 minus sine of pi dash CS is equal to 18 times sine of pi dash CS. So once you will rearrange it, you will get sine of pi dash CS is equal to 3 by 19. This 18 plus 1 is 19. So 3 by 19. So pi dash CS will be equal to sine inverse of 3 by 19. Fine. So you were asked to determine the friction angle. So we started with the M, which is the slope, Q by P, which can be also written, written in terms of the 6 sine phi divided by 3 minus psi phi. And we know that Q is given by M times P, PCS. Fine. The mean effective stress is 100 kPa for triaxial shearing. The diametric stress corresponds to tension cutoff line. So we know that if we have a, for example, if we have this uh, state, for example, D dash, and this is the critical state line. This is the peak state line. So the cutoff is this D, this slope of 3:1. Fine, as you have seen in the last lecture, in the last few minutes. So if we have Q, we know that the slope Q by P, Q by P is equal to 3 for the tension cutoff. Correct? So if P is 100, so Q should be 300 kPa. Correct? So this is the mean effective stress for like the diabatic stress corresponding to tension cutoff. Beyond this, we can't expect a state in the tensile, or we can see that there will be a generation of tensile force in the sample. Now, an odometer test gives lambda is equal to 0.25. So it is given that lambda is equal to 0.25. Find the compression index. So we have seen that how we have determined the CC, which is given by like change of E divided by uh, I think 2.303. Oh no, change in this divided by change in P. Wait, forgot on this. CC divided by 2.303 D of P dash. We have done this. Yeah, here we have seen, yeah, change in E divided by change of P. So here you can see CC is got change in E divided by change of log of P dash. Then DE can be represented in terms of specific volume. Then this log of P dash. So we know that, see, ln of P dash can be written in terms of 2.303 log of P dash. So if we differentiate both to the both sides, D of ln of P dash can be written as 2.303 d of log of p dash, and this d log of p dash is given by 1 divided by 2.303 d ln of p dash. So on differentiating this d ln of p dash, we will get, so you will get p dash divided by like P dash divided by dP dash. So once we rearrange it and use the equation of specific volume, we will get the value Cc is equal to 2.303 lambda. So we will get Cc is equal to 2.303 times lambda. So that is 0.25 into 2.303, which is equal to 0.5. So we have represented the compression index in terms of critical strength parameter lambda. Test. Peak shear stress is 250. Normal stress is peak shear stress is 250. Normal stress is 200, and 5 CS is 32 degrees. Find the dilation angle. So we know that if we represent this equation formation, I guess we have discussed it in the previous weeks also, or previous topics also. We know that tau peak is given by sigma dash p into tan of sigma dash p tan of phi dash cs plus phi dash peak if it corresponds to the RT. This is a dilation angle corresponding to the peak state. Now tau peak is given by 250. Sigma dash p is the 200. It's tan of phi dash cs plus phi dash. So it implies tan of phi dash cs plus phi dash p is equal to 250 divided by 200. So it is uh, like phi dash cs is 30 plus phi dash p is equal to tan inverse of 250 divided by 200. So it's 30 plus phi dash p. Tan inverse of 250 by 200, you will get 51.3 degrees. So phi dash p is equal to 51.3 degree minus 50 degrees. So phi dash p is given by 90 degrees. Fine. So this is the way how we calculate the dilation angle from the information corresponding to the peak state. Now a soil has a specific volume of 2.2 in critical state. Specific volume is 2. Determine the state parameter and comment on the behavior. Now uh, let us talk about this. It is this line corresponds to the critical state specific volume, or the specific volume corresponding to critical state V naught Vc. It has a value of 2. It has a value of 2. uh, Correct. So it has a value of 2, and a soil was there when you start initially doing a test. Its specific volume was 2.2. So V naught was 2.2. Since this point V naught lies above the critical state specific volume 2, this soil has a tendency to reach the critical state by decreasing the volume. Fine. For example, uh, uh, it's like if we draw this is the critical state line. Fine, and this point is somewhere here. Fine, and this point will reach the critical state line by decreasing the specific volume. So the state parameter phi is given by V naught minus Vc. That is 2.2 minus 2 is positive 0.2, which means that the soil is loose and it has a tendency to contract during drain shade. Fine, fine. So state parameter determine the state parameter phi size is equal to V naught minus Vc, and it's a positive value when we plot them in the graph. Let's say with the sigma. It means that this soil has a tendency to reach the critical state by decreasing the volume. Correct? Fine. Because it's a we can say that during a drain test and the sigma I remains constant, then it has a tendency to reach the critical state by decreasing the volume. So it has a tendency, it's a kind of a loose material which has a tendency to contract. Now NC clay sample is isotropically consolidated at an initial mean effective stress of 250. Fine. So it is given that phi dash P dash initial is 150 kPa. Sorry, 250 kPa. The sample is subject to undrained compression. The initial specific volume V naught is equal to 2.1. Critical state parameters gamma is 3.1, lambda is 0.25, and phi dash critical state is 28 degrees. Determine the pore water pressure at failure. Now we have been asked to determine the pore water pressure at the failure. Now since it's a like initial, if we talk about the initial state, mean effective stress is 250 kP, and once we are doing the undrained change, we are not changing it. So the change in the sigma 3 is 0, correct? And sigma 3 is the confining stress, which is given by 250 kP. Please note this. Or we can write it as equal to P naught. P naught. Fine. Now, since this is undrained compression, so the V specific volume initial will be the specific volume final given by 2.1. Correct? Now, for the CSL, we know the relation V is equivalent to gamma minus lambda times ln of P final dash at the final state. So V final is 2.1, gamma is 3.1, minus lambda is 0.25. We'll be able to find the final PF dash, which is the final mean effective stress. Correct? Fine. So we'll find, so this PF dash is equivalent to e raised to power 4, which is equivalent to 54.6 kP. Fine. Now, using the slope of the critical CSL line, M is given by 6 of sine of phi divided by 3 minus sine of phi dash. It's also equivalent to Q final divided by P final. Fine. Why we want to use this? Because we have one relation which we are going to use, for which we need this QF. So with this equation, you will find this QF, which will be equivalent to 60.6 kPa. Now the final PF dash, it will be equivalent to the, what is the initial P naught plus what is the increment in the mean effective stress during the sharing. So that is actually given by P naught dash plus QF divided by 3. Fine. This is like you can find like this. P is equal to sigma 1 plus sigma 3 into 2 divided by 3. Correct. And this Q is equal to sigma 1 minus sigma 3. If we replace sigma 1 by sigma 3 plus Q, if we replace P, like the Q is equivalent to sigma 1 minus sigma 3. If we replace this sigma 1 or any of the two, so as to bring this Q there, so sigma 1, sigma 3 is equivalent to, or sigma 1 is equal to Q plus sigma 3. So P is equivalent to Q plus sigma 3 plus 2 times sigma 3 divided by 3. So it is P plus Q by 3 plus sigma 3. Now, at the final state, we can write QF, PF is equal to QF divided by 3 plus QEF. Now, since mean confining stress is not changing, so this final sigma 3F will be equivalent to sigma naught, or the initial mean confining stress. So that's why the final mean effective stress is equivalent to P naught Q, P naught dash plus QF divided by 3. So P naught dash uh, can be written equivalent to P naught dash is 250 plus QF is 60.6 divided by 3. So PF dash is equivalent to, it's equivalent to 270.2 kP. So what is the final pore water pressure? The final pore water pressure equivalent to PF dash. This was in terms of like the total mass effect kind of thing. So PF is 270.2 minus PF dash is 54.6. So this is in terms of total stress parameters. So this is in terms of effective. That's why, like some of you might think that why we need is P dash P dash F. So this why we are doing it two times. So this is in terms of effective parameters. So we want to know the P in terms of the total stress parameter. So that is difference between two will give us the pore water pressure. So that's why we have used this equation PF is equal to P naught plus Q by 3 in terms of total stress parameters, because QF is independent of the pore water pressure. So we'll get PF is equal to 270, and pore water pressure that is generated and during this shearing process is equal to 270 is the total mean effective stress minus effective mean stress pressure, that is 54.6. You will get 215.6 kP. So it means that the final pore water pressure UF, pore water pressure at failure, is given by 215.6 kP. So this is all regarding uh, this problem, example problems. So uh, I think whatever the questions you will face or you will see in the assignments, you will be able to answer all of those if you carefully understand the concept here, and you are carefully doing the things in a correct way and using the correct expressions. So you'll be able to solve all those questions very easily. And most of the questions that you face in the assignments, they are very similar to what I have solved here. So that's all for today. Uh, we'll be meeting on next Saturday. Uh, Till then, you check the notes. If you have any doubts, you can just ask us in the forum where you can. We have a dedicated team to answer you. So till then, enjoy this course, do the assignments properly, and get back to us in case you have any doubts. So I will be stopping the recording here, but the meeting will be up to 5. Will continue up to 5 p.m. So for the doubt sessions. So if you have any doubt, you can reach out there. Thank you.